All right, good afternoon, everybody. Welcome back to the final day of discrete math. I didn't even write a plan down. That's how confident I am. Plan for today, we're going to do presentations on this worksheet, and then the second half of class, talk about whatever you all feel like. Office hours. I am going to have office hours next week. I still need to actually choose them. So probably tomorrow sometime you'll get information on that. Planning on doing some office hours, probably like Sunday through Thursday. Maybe even Friday if you all play your cards right, so we will see. Also, don't forget, proof portfolios due Monday. Laura?
Yeah, I have to look back. I think I have a question about the recursive problem. I wasn't exactly sure what kind of problem to do for that. I will look at that and have a specific question for you later. Okay?
Cool. Any questions before we get started for today? So, I got one here's a winter themed one. Suppose you're indoors and the power goes out and it starts getting really cold. Where should you go to warm up? Lily?
Corner, right?
Always go hang out in the corner because it's always 90 degrees there. All right. Well, let's see.
Know where my dad is cheap question.
Yeah.
Wow.
So hyped.
Oh,
I don't want to go inside out for that one. I was stressing you out. I think it wasn't that bad.
No, it wasn't bad. Interesting.
It was
Sorry, Laura.
I always love that part now because it's just, I don't know. About her. It's fine.
Man, last chance. I have to think carefully if I want to do this.
I like Sophie personally.
I agree.
Oh yeah. It's not intentional. It's like a very capital S.
Yeah.
Like, in case you were wondering, because sometimes it's hard to tell.
No, yeah, it's like an aggressively capital S, man.
Okay. Griffin, get things started for us.
Nice.
Out of those four, you presented the least recently.
This is what I was thinking.
Yep.
Euler circuit 3 packet.
Hi, my name is Griffin. Alright, so for the first problem, we are supposed to use the flurry algorithm, as described on the first page, to find an Euler path in the following graph, and then write down a path. So I'll draw this up for y'all. Your attack chair's in the way. Alright. Okay. I decided to start here. I labeled this A, B, C. Yeah, I didn't do anything fun like Laura. Math, not drugs, just went through the basic. Unless you want me to write out with the arrows, I simply followed the edges in the way I numbered them. So I started with A, went to B, to C, to D, to E, to F, to B, to A, to G, to F. Any questions? All right.
Question.
Yes.
Are there any Euler circuits in this graph?
Are there any Euler circuits in this graph? Well, so we know that the definition of an Euler circuit has all even vertices. And we have two, because it is path, 2 odd vertices at F and A. So unless you wanted to remove either edge E7 or, actually that's still, if you removed edge E7, you wouldn't even have a path. So, no, in short.
Okay.
Yep.
I think you could make that if you remove E6 and E7.
Yeah,
I
you
think
have
we
to
do.
just remove 2 because to get down to an all even number of edges. All right. Thank you.
Thank you, Griffin. Next up, we have Sophie.
Yeah, Sophie.
I'm so first.
I feel like I'm just gonna acknowledge I couldn't show the last presentation.
Oh,
I don't know why.
Oops.
I know. But thank you. Thank you.
Okay.
All right, so
Hi, I'm Sophie. And do you all want me to? Would you rather I draw the graph or I write out my steps?
Graph.
Okay.
I say, because someone else may have labeled the graph differently for me. I
Oh,
think
true,
I think
true.
the graph would be-
That's a very good point. That'd be highly problematic.
Texas, though, right?
Okay, so there's not really a rhyme or reason to the order that I labeled these in. I had A, B, C, D, E, F, G. And then my path was from D to G. Actually, I'll label the edges. E1.
If you want, maybe could you like trace out your path on the graph?
Yeah. Okay. Should I label the edges, or does that add anything? I don't think so.
Just trace the graph, that'll look good.
So I went from D to G to C. What? Oh, I mislabeled. This should be G. This is F. This is just getting messier and messier. I'm sorry. Okay. D to G to C to B back to G to F to D up to E to A to B and then back to E and finally back to F. Any questions? Holly?
So, given that we have 2 vertices with odd degrees, is there any other place that we can start on this graph besides D?
Well, I guess we could start on the other one that has an odd degree, which would be F. Right?
Okay.
Anything else?
Yeah, then you can just do her exact same path backwards to have a path from F to D instead of D to F, for instance.
Dr. Driscoll?
Are there any Euler circuits in this one?
No. Because
Just leave it at that, just watch.
Answer.
Leave it at that.
because there are odd vertices, so.
How many edges would you have to remove to make it an Euler
Um,
circuit?
Just one, I think, because if you took the edge between F and D, because these are the only, I'm pretty sure these are the only odd vertices, and then that would make both of those even, so then there'd be an Euler circuit. Thank you.
Thank you, Sophie. All right, next up, Isabel. She's gonna prove for us.
Alrighty, hello. So I'm explaining why Flurry's theorem proves the following two, I guess just the last theorem. It's the second Euler circuit theorem that says if an Euler graph is connected and has exactly 0 odd vertices, then it has an Euler circuit. So to prove this, I used 2 theorems. Is it okay if I don't write out Flurry's theorem since we have it? Dr. Gerstle, is that
You
okay?
could say, you could just say like by Flurry's theorem, we know that, and then what you want to use it for.
Okay, so for the first part, by Flurry's theorem, we know that a connected Euler graph with exactly 0 odd vertices will have an Euler path. Also, my handwriting is atrocious, so apologies, but I can't do anything about it.
That's what you call atrocious, I'm jealous.
Really? She's pretty rough. And then for the second theorem that I used, I referred back to the Euler circuit packet 2, where we talked about the even vertex theorem, which says that if B is an even vertex, then every Euler path that starts at B must also end at B. And I'll write on the board in a second, but basically my logic with this was that if we have an Euler graph with 0 odd vertices, we know that there's a path, and then whatever vertex that you decide to start at, there is a path that you can also end at that vertex, which would make it an Euler circuit. I'll write that on the board. Okay, sorry, that was a lot of writing. But, yeah, basically because we know that we have an Euler path, and then also that you have to start and end at the same vertex, you would have an Euler circuit. Does that make sense? Are there any questions? Dr. Gerstle?
No, I'm trying to think of a good zinger of a question, but nothing's coming.
Okay, all good?
Thank you, Isabel.
You're tough, son.
Nice job, I like it.
Oh,
And
kill
for the final presentation of the semester.
Yeah.
Don't screw it up.
Okay. So for this one, we're looking at that bridges problem. And if you label the landmasses as the vertices of a graph, we can visually draw it out using our graph notation like this. So I call this B, C, D. So there are two bridges from A to B, two bridges from B to C, one from B to D, one from A to D, and one from C to D. And then by Flurries' theorem, which we just erased, you have to have either 0 or exactly 2 odd vertices. So to start the proof, you can look at the degrees of all these vertices. So the degree of A is 3. The degree of B is 5. Degree of C is 3. And the degree of D is also 3. So this problem does not have a solution using Flurries' algorithm. So there are no paths or circuits connecting the land masses or between the vertices. Yeah.
I have a question. Ollie, what's your question?
Oh, I was gonna say, would there be some edges that you could remove to at least make a path between?
So you'd have to get it so that there's probably be easier, I think, to get it so that there only be 2 odd vertices. So if we check out,
Could you take out like the middle?
yeah, I'd say if you start by taking out this one, B and B, yeah, perfect. A now has 3 and C has 3, but B has 4 and D has 2. So there's a path there. And I guess I can make a circuit too. That's how you know I've made it to the end of the course. I can do math like that.
Oh gosh, when you put it that way. What theorem tells us that if we have 4 odd vertices that we can't have an Euler path?
Flurries' theorem.
Flurries' theorem says that if we have 0 or 2 odd vertices, then we do have an Euler path. I don't think Flurries' theorem though tells us anything about how if we don't have either of those cases, then we can't possibly have an Euler path.
Yeah, now I'm out of my league.
I wrote down provide first Euler path.
Ooh, because the first Euler path theorem says that if you have an Euler path, then there has to be 0 or 2 odd vertices.
Yeah.
So therefore, if you don't have that, then you can't have an Euler path.
Yes.
I like it.
Okay.
Yeah, I would say I think that's the
Is that
theorem
one of the
that's
last
being used.
packet? Okay.
Right. Any other questions for Griffin? Now's your last chance.
If you added,
Yeah, Griffin.
if you added
Of course.
more, if you added more bridges, could you possibly create a path from that?
Look, I gotta think for a second. We gotta get them all, or we gotta make it so that 2 of them are, yeah. So that's now 6, and that's now 4. Now we have a path.
I have a hot take on this one. I think if you remove any one bridge or add any one bridge to the original problem, it would make an Euler path possible.
That's so sad.
I couldn't forget it so wrong.
Well, because I know there's like no possible path, but I just want there to be a path so bad. Like I feel like there's just one we're not thinking about somehow.
Unfortunately, I think Jacob is correct that there is not one.
Yeah.
All right, nice job, Jacob.
Oh, thank you.
All right, nice job, everybody. Turns out that now everybody who is currently present has either 9 or 10 presentations. So good job. Really good job over the course of the semester, I thought, with stepping up to the game here. So yeah, I decided with like half a class left, I didn't really want to introduce any new ideas. There's another I had another couple of graph theory packets I would have done if we had more time, looking at graph colorings and the 4/5/6 color theorem for a graph. Really cool kind of discrete math result if you have any interest in it. Feel free to look it up. 4-color theorem is something that was basically proved by a computer by looking at like thousands and thousands of possible cases and proving that all of them end up being okay. So if something is only proven by a computer and nobody's actually ever proven it by hand, by any human being, do you consider that to have been proven? Laurie?
Couldn't there be like examples that the computer hasn't looked at that could be false?
Let's assume that the computer has looked at every possible case. Maybe not every example, but every kind of possible scenario, type of scenario that could occur. I don't want to get into too much the details of how that works in this specific case, but let's assume the computer has covered all the cases.
Are you assuming that humans program the computer and wrote the code to like solve this problem?
Humans programmed the computer with code to check every possible case, and then the computer came back and said, hey, every possible case checked out.
Then I would say that that's kind of like indirectly proven by humans. If the human would have made the error, I don't think the computer would have made the error. So I'd say, yeah, computers just do what we tell them to.
That's like say, if I told a computer, if I told my calculator to tell me what 8 times 9 is, and it told me it was 72, does that make 8 times 9 72?
Well, no, because there's a program behind. I mean, yes, that is true, but it's the programming behind it, because there could be an error in the program that someone wrote. But so I guess yeah, it still comes down to human error.
As long as the program's right.
If the program's coded correctly, then we can consider that to have been proven.
Yes.
Let's assume we have a team of mathematicians who pored over that code and checked off that the program does run as intended.
I mean that not that only that it runs as intended, but that it's like
And that it's all programmed
represents-
accurately.
Yeah. Okay. Yes.
I think. So wait, has it actually checked every single possible case, or has it like checked every case so that it's like understood to be recursive, even like?
Actually,
Because like I know with
it's
like.
checked every possible case.
Oh, okay. Well, then that's probably fine. I was thinking of like the whole idea of like a proof to say that like prime numbers are infinite, and like people understood it to be true long before it was proven to be true. So like I don't know if that. I think whenever someone says like there's a computer involved, I feel like it's one of those instances where it's understood to be true but not completely proven. If that makes sense.
I have a problem for you.
Okay.
Not specifically for Laura, but for the class. Yeah. Wait, how does this work? Hold on. I don't remember my own problem. Hold on. I'll have to play and talk about this. Hold on.
Your coefficient on the x term has to be 41.
Okay. I claim no matter what integer you plug in for x.
No.
F of x is not a perfect square.
Rescind your statement about that not being correct, Alex.
I thought he was going to go for something different, but I kind of see what, yeah, okay.
We plug in x equals 1. 1 squared minus 1 is 0, plus 41 is 41. That ain't a perfect square. We plug in x equals 2. 4 minus 2 is 2, plus 41 is 43. That ain't a perfect square. By the way, when I say perfect square, I mean something that's not like 4, 9, 16, something that's the square of an integer.
Oh wait.
What about 41?
If you plug in 41, why does 41 work?
Because that's x squared.
Because then it just comes out to 41 squared. Because the minus x and the plus 41 will cancel each other out. Point I was going to make with this though, you plug in any integer from 1 to 40, it doesn't work. Nothing from 1 to 40 will produce a perfect square out of this. But 41 does. So when we say that math people have understood result x to be true for a long time, that usually means that, oh, we've checked a lot of different cases, and it turns out that in a lot of that every single case we checked, it turns out to work out. How do we know? We just haven't checked enough cases yet. Before it was proven, how do we know we haven't just checked and shown that? How do we know that there could just be a finite number of prime numbers where that finite number is really, really, really big?
I guess that's when you have like real humans with real thinking brains to kind of like look at this problem and be like, yo, what about 41? You know what I mean? Like, so
Yo!
So instead of just like having the computer run all the numbers, you can just kind of theorize it before you do the dirty work.
All right, fine. How about this? No human has looked at this code, has actually looked at the results produced by this computer and verified that every result it's checked is correct. Oh, Mariah, you're making some interesting faces.
So, wait, at the beginning, when you were saying that the computer has checked all possible cases, even if it hasn't checked like every single possible number you could plug in,
Well, let's talk about what this theorem says, so I can kind of maybe explain what that means a little bit more. Basically, what this theorem is if you have a specific type of graph called a planar graph, which is basically, think about it as being like a graph where none of the edges intersect each other, or a graph that's at least equivalent to one, where none of the edges ever intersect each other. Let's say, I don't know, something like this. At each vertex, we're going to give it a color. So, red. And the trick is, at each vertex cannot be the same color as any other vertex that shares an edge with it. So since this vertex shares an edge with this one cannot be red. Now, let's make it green. What color would you like to make this vertex?
Green.
Yellow.
I heard green first. Okay, how about this one?
Turquoise.
What's that? Turquoise?
Purple. Yellow. Red.
All right, how many colors did we use? 1, 2, 3, 4, 5. Turns out that what this theorem stated, the 4-color theorem, basically says that given any planar graph, no matter how big or complex, you can always color it in this way with using only 4 colors.
Oh wait. If you have like a wheel, like an old-fashioned wagon wheel.
Like this.
Oh wait a second. Never mind.
I can do that one with 2 colors.
What if they're all like intersecting on the outside?
Like that?
Yeah. Oh shoot, Dr. Nerd.
That one I could do with 4. So when I say a computer's checked all possible cases, I not mean a computer has checked every possible graph, because obviously there's infinitely many graphs you could produce and have to check. What I mean by that is when computers check thousands and thousands of cases is it's gone through and checked like all possible configurations of what if we have a triangle in our graph? What if we have two triangles next to each other? What if we have a triangle next to a quadrilateral? What if we have a quadrilateral next to a triangle next to a pentagon? And basically checked like all possible configurations like that. That's kind of what I mean. By the way, the packets I was going to give you if we had time, you all were going to prove that you can do it with 6 or fewer colors, any possible planar graph. And then to show that you can do it with 5 is a lot harder, but it's possible. And then to show that you can do it with 4 is a lot harder, but it is possible.
That would have been the proof portfolio.
I think even the 5 case would have probably been too much for a proof portfolio problem. That would have been like a packet in and of itself just to prove. For a proof portfolio problem, that would have. No, because I don't want to grade that. I'd have to program my computer to grade that one for me. So, it's a question. Can we do it with 3?
I think Aaron once told me you could, so that's pretty good for me. I trust Aaron.
If Aaron says it must be true.
Yeah, he was talking about it in research. We were supposed to be working, but we weren't. He was blabbing about some colors and graphs, and Carl and I were throwing a golf ball on the wall, so.
That was the
Yeah, they were just telling us some stuff, and we were just vandalizing. I see you pointed to this one.
Yeah, because we used 4, right?
we used 2.
Could we have done it with fewer? We used 4 here.
Right.
Could we have done it with fewer?
Based on the fact that you're asking,
You couldn't.
it's yes.
Oh yeah, what would you use? Can't use blue, green, or red.
So let's see. All right. What about now?
But
I'll
you
leave
have
the
blue.
blues.
Oh my goodness gracious!
Oops.
There, I solved that issue.
No.
Uh-oh.
Is he trying to prove what?
There, I just solved that issue.
No.
There, okay, you all get what I'm trying to, yes, I'm trying to prove a point. Turns out this is a graph that you need at least 4 colors for, no matter how hard you try.
But what was wrong with our unconnected wagon? Like, I guess it's a different, like,
With just this one?
yeah, I think I missed
Well, this one, if the edges aren't colored, I think this one you can actually do with just 2, because since like these 2 don't need to be different from each other like they do in this graph. I screwed this one all up. You could just make all the outside ones the same because they're only connected to the inside. So this one you could do with just 2 colors. It turns out that the proof that the computer came up with is that 4 is that no matter what planar graph you're looking at, you can always do it in 4. But it turns out there do exist planar graphs like this one that do require at least 4, so that 4 is sort of the magic number going on here.
4 is cosmic. Sorry. It's a word game.
Adam.
I was just gonna ask about if it's exactly for at least 4, but like, does that
It's
simple wagon wheel, does that fit the criteria of the problem? Or is it different?
The wagon wheel does require 4.
Okay. Or no, the unconnected one. Like
The unconnected one does.
two.
The unconnected. You mean like the top left
The
one?
top one without the ones around the outside.
The one that was a person briefly.
Yes.
That one you could do in 2.
Yeah, but does that fit the, like, with the computer, I've looked at a case like that, would that like, fit the criteria for that problem? Okay.
Yeah. So when the computer said like it checked all possible cases and 4 is what it spat out, that doesn't mean that there weren't cases where you could do it with fewer than
I
4.
wasn't sure if it was exactly or.
Yeah. 4 is just what's necessary in order to be able to handle all possible cases. Some of which you could do with 3, some of which you can do with 2. And if you have a completely disconnected graph, and a graph with no edges in it, you could do it with 1. But Dr. Gerstle, I hear you say, what about this one?
Those intersect.
If you allow your graph to have edges that intersect each other, then you might need more than 4. Like if I have 5 vertices, all of which touch every other vertex, you need at least, well, you need exactly 5 colors to get the job done.
Do they have to be straight lines or can they curve?
Hey, Kurt.
So then you don't need any intersections. You can just curve on them and then you can disprove.
Can you now?
What?
Can you now?
I don't know.
All right, Holly, I challenge you to try and do that.
I think she's right. You just
No, you just
drawing
go
those
outside,
things all the
just
way
keep
around the
going further.
chalkboard.
Yeah.
All right, so let's take this edge and now it's going to go outside like this.
Yeah, there's 2 across the.
All right, let's try this edge. It's going to go like this now.
Yeah. Well, it just depends on the angle that you.
Turns out, try as hard as you might, you can't get it done. You can't draw this in a way that makes it planar.
That's sad.
Unless Helen Mariah thinks it's the other way.
Wait, but like if we just erase that other one, the one that's like is currently intersecting them, then can it still be done with
Which one, like
4?
this one?
It'll go on the outside.
If every vertex is connected to every other one by an edge, and you have at least 5 vertices, actually call that a perfect graph, believe it or not, can't be done.
But you're saying
So
if that
we
one didn't
disconnect-
exist.
So if we disconnect the bottom one and the middle.
You're saying the problem one?
Yeah, the
Why don't
one.
you draw what you mean? Because I'm not sure.
Just like if I'm erasing that drawing. If we just erase this one, then can it be done with 4 again? Like do we want to do 5?
Sure, but how are you going to get? Sure, but then that's not the.
I think I'm just worried like the bendy things are like
Yeah.
completely fine. And then
The
it
bendy
works.
things are completely
Okay,
fine, but
okay.
the problem is if you erase an edge, then that's not the same graph anymore, and then
Yes.
it becomes something that is
Right.
planars, and then therefore going to be 4 colorable.
Okay, cool.
4
I
colorable
just
means
looked
you
a
can do
lot
it in
more
4 colors. Turns out that there's a lot of fun math you can do, including Euler's formula for vertices, edges, and faces of a graph, which is something we didn't get to, that allows you to kind of prove these sorts of things. And if we had an extra week, we would prove that you can always do it with 6. So fancy induction can be done.
Might be off topic, but I figured out my specific question. about
Imagine that.
the Portfolio.
Add to that. Let's something like that's relevant to the rest of the class or to you.
I mean, it might be, I don't know.
What's your question?
So like in the recursion packet, it's like a recursion proof, but we'll probably be doing that inductively, right?
Yeah, so when I say a recursive proof, I just mean anything where like you're defining something recursively and then probably proving it by induction. That can count as a recursive proof or an inductive proof,
Thanks.
But not both.
but not both. Indeed. I'm a mathematician. I was gonna careful how I phrase that.
Wait, I actually do have one question. Because I get this wrong on every proof. I don't know why my brain doesn't understand it. How exactly are we supposed to do the base case when we're given a recursive formula? Like, what do you want us?
It depends on what the problem is. So if I were to give you something like A1 equals 1, A2 equals 4, A3 equals 9, A for n greater than or equal to 4, A sub n equals A1 minus A2 plus A3. There's something sort of like that. I forget what that exact formula is. Prove that for any n, A sub n equals n squared. For this one, I think you would need to handle these 3 as base cases specifically, because those are the ones that are not being defined using your recursive step here. And for those, you just say, oh, well, A1 is clearly 1 squared, A2 is clearly 2 squared, A3 is clearly 3 squared by definition. Boom, base case done.
So that's all, we don't have to put like the case, like the
For?
first case that you're using the rule for?
Probably not, because A4 you could already, because like for A4 I think can already be considered part of your inductive step because it's going to be defined using the recursive formula. And so if you know it's true for A1, A2, and A3, that'll show that it's true for A4.
Okay, thank you. Yeah, that's definitely the exact problem that I got wrong, so.
If you're in doubt, you could always do A4 as part of your base case. It wouldn't be wrong, it would just be unnecessary.
Okay.
When did you begin saying words like gadzooks and groovy?
I don't understand the question.
Like, when did you start using those words?
I've always used those words.
Forever?
500 years ago, I was using
He
those.
said that's. I was talking
I don't know. I grew up using those words. I don't know. I got some hippies in my family. What can I say? Perfect.
Do you have a proof of your theory about the Königsberg bridges that if you add or subtract one?
Sure. Here's my proof. I'm not going to write down the proof, but I'll say it out loud. All of these are odd. I guess you have to have an edge, a bridge that connects two different islands. You can't have a loop, because if you have a loop, then that doesn't change anything. Like, I'm just going to have a bridge that kind of goes a scenic route over the water and then goes back to the island it started at. Because if we were to add any edge between any two islands, I don't know, pick it. Griffin, give me two of these.
A2 and A4.
Groovy. We have a bridge from A2 to A4. We're going to add one to the degree of A2 for where the bridge starts. We're going to add one to the degree of A4 for where it starts. Therefore, these two become even. Now we have exactly two odd vertices. Therefore, there's an Euler path between them. Alternatively, if we subtracted a bridge, same thing. You would subtract one from the degrees of two of these vertices. Odd would become even, and then therefore you once again have exactly two odd vertices. There's going to be an Euler's path. Neato mosquito.
That one too.
Awesome possum, neato mosquito. I had a friend when I was in college who I just started calling awesome possum one day, and then it kind of became a thing, and other people started calling her awesome possum too.
Oh, so it's like peaches.
Sort. I don't know. How did he start becoming called Peaches?
Well, his name is Ethan Cobb, so all through high school people called him Corn Cob, but then Rowan called him Peaches, like peach cobbler, and he liked it because we weren't calling him Corn Cob, so it stuck. He also kind of looks like a human peach because he's kind of like shorter and kind of round and kind of like, he's got kind of red cheeks and he wears salmon colored shorts, so.
When
he
you
wears
put it that way.
Scooby-Doo t-shirts, so I think it
I
fits.
don't listen to this.
He has like 12 different Scooby-Doo t-shirts. It's kind of impressive.
Anyways,
Those summer tank
I don't know. This is just someone I just started calling awesome possum for no real reason, and it stuck.
Wow, real trendsetter.
Have you ever had a nickname?
Yeah,
What is it?
I've had many nicknames. I don't know. Dr. G. I got my first students came in my first semester here. I think that was like Elaine and Steve Weiderman.
Steve Weiderman.
Yeah, started calling me that. I don't know. Kevbo. Go Kaiwan. That was my Chinese name. K-Slice.
That's awesome.
I'm not telling you that one. Lots of nicknames.
Have you seen the movie Mean Girls? There's a character in there named Kevin G, and he's like a math guy. And so I always think about that. He's also an MC.
Oh,
But yeah, he's a big math guy.
Neato.
Mosquito.
Burrito.
Magneto.
Dorito. That's cool. I don't know. I know when I started getting called KG is after Kevin Garnett, a basketball player, but I don't know. I'm more of a math person than a basketball person.
You're pretty tall, you could probably take him on.
Yeah, but see, there's also something else that's needed. It's called
Just hit him with your meter stick.
hand-eye coordination, among other things.
Throw chalk at him. The element of surprise.
That's
Nice.
nice. Just gonna throw the chalk around now.
Could you imagine?
I have my golf ball.
I have a calculator.
Yeah, this is what we do in research. We clear all the desks out of here and just start bouncing this thing around.
And see how many we can get to.
And sometimes you blindfold yourself. That
Or
one
do
was
one
scary.
eye. The one eye was the
It
worst.
hurt. We all got like
really
headaches.
dizzy.
Got like really dizzy. Like
Because you lose.
I need to have a chat with Dr. Bowles about this.
I feel like getting a lot of research.
hey, I will write a
You
thesis that will be at least 5 pages long.
I'm making Abby write an outline that's 5 pages long.
Dang.
That probably actually worked.
Anyways, any other questions about, like, discrete math?
Or nicknames.
My personal one.
Do you have any pets?
I do not at the moment.
Have you had any pets since you moved to Hillsdale?
I have not.
If you had a pet, what would you get?
Dog.
What kind of dog?
Fun.
What would you name
So,
it?
a dog. I don't
You learned.
know. I get 2 dogs named one Euler and one Wakelet. And one Vertexes.
Hey, that is a legitimate word now. I've gotten people to start saying that. It's going to be a thing in 10 years. Just
Alright, Adam, riddle me this. What's the plural of octopus?
Octopi.
Incorrect.
Really?
Really?
Darn. I'm not a marine
Oh, there's 3
biologist,
different correct ways, isn't there?
scientist.
There's
I don't
2.
remember. 2?
The only
Octopi is not
octopus
one
I've
of
ever
them?
seen was fried.
Octopuses and octopode.
Octopode. Wow.
I
So
swear.
that means
Where did
my-
octopi come from? Because I swear I've heard that before.
It came from, there's a lot of Latin words that that end in us that you pluralize by making it I, like radius, radii, cactus, cacti, octopus, octopuses.
Yeah, so my vertexes thing holds.
No, that is a completely different case.
I'm gonna roll
So
with
is
it.
octopus not a Latin word? Wait, yeah it is.
I might be mistaking Latin and Greek.
It's
I
all the same.
need to get Dr. Warden here to explain this for me.
Can you speak Chinese? Like, do you know how to?
OHOEDR.
He was on the panel for the China CCA, like, at some point.
I did not go to that CCA.
While I
so
was
I'm
here.
a first semester freshman. Didn't know what a CCA was.
I didn't know what a CCA was either, and I agreed to do it.
Did you get any really good questions?
Oh,
on
God.
CCA?
Really good questions.
Like
It
any
can be lots
donors
of
that
different
ranted
things.
for half an hour, it was more of a statement than a question.
Those don't come to the faculty panels. Those just go to like the actual talks.
That's
Thankfully, someone did ask me some like really self-serving question. I don't know how I would have answered.
To them.
Oh, these CCAs, man. Get some interesting stuff happens.
It is wild.
I have not done a CCA since.
They leave all the really good desserts on the tables if the donors don't eat them, so it's just great to go to them just to grab that afterwards. That was the biggest takeaway I got from my CCA.
Good to know.
I took the AI one though, that was dumpster fire.
The what one?
The AI one our freshman year. Yeah, it was a clown show.
I'm not surprised.
Yeah.
Okay, well, we have like 2 minutes left, so one more question. All right.
Tell us your deepest, darkest
My deepest, darkest what?
your fear or your fears.
Okay, I can answer that one. My deepest, darkest fear. Okay, well, what's the deepest, darkest one I'm willing to share? I don't know. I fear that one day, I don't know, my usual massive case of imposter syndrome where I'm afraid that like I am no way qualified for what people think I can do, and one day they'll realize that I'm a complete fraud and bad things will happen.
Do you know your Enneagram type? I doubt it, but.
I don't know.
Okay, it's a person, it's.
I know what an Enneagram is. I've never.
You should take one. I'd be curious to see
Anyways,
what you
I
get.
guess very common in academia in general. What's your Enneagram?
Oh, that is extremely common in academia in general.
I went to this grad school panel and literally
Dr. Rose is like, yeah, everyone thought everyone else was smarter and knew what was going on.
But
I always get
Themselves knew what was
those
going on.
monograms where you put your initials on stuff. I get those mixed up.
Yeah, I'll be honest. If you, for anyone in this class, if you've ever thought that like you have no idea what's going on in this class and that everybody else is so much smarter than you and knows what's going on a lot better than you, for all but like one or two of you, you would be wrong. I'm just kidding.
Dang.
Common thing among high achievers in general. But yeah, no, my deepest, darkest secret is I live in fear that one day they realize that oh my gosh, one day they realize that I know so much less math, like theoretical math, than like Dr. Gabler and Dr. Murphy, and they're gonna find out and fire me.
That won't happen though.
yeah, that's not true.
I feel like you're okay.
Oh
I'd say you know a lot of math.
no. Well, we'll see how the next month goes.
Say if you got your doctorate, then you should be okay.
Yeah.
Ha, I could tell you about lots of people with doctorates who don't know any math.
I mean, isn't the issue with because you get so specialized?
Say what?
Like, I mean, because isn't the whole thing of like you could get so specialized that like you might not actually know how to do Calc 1. I mean, at one point you took the class or whatever, but if you're getting like.
Oh yeah, no. I could tell you the point in my life where I knew the most math, breadth-wise. Right before I took my qualifying exams at the end of my first year of grad school. Because I had to know so much math at that point.
That's what I've heard from
And then like after that, then you can start specializing in like, I don't know, now I can't do analysis anymore. I'm looking forward to having a lot of you for real analysis. Alright, we're gonna call it there, but seriously, this has been a really fun class. You've all been great to work with. Thanks for putting up with all my unreasonable proof portfolio mistakes journal demands, and yeah, I'll send you my office hours this weekend, and good luck with the final, good luck with everything. You all are cool.
Do you have office hours now?
Um,
If you do, I could turn my proof portfolio in today.
Like,
I'm not gonna read for it. Can we postpone towards like Sunday, Monday? A couple meetings I already scheduled for today, and I
Good title page.
a lot of.
All right.
With a really fancy title.
oh,
I like that you didn't even type that.
Okay. Oh, hey. Oh gosh, I recorded it. I can't post it.